Dr. Barker studied computer science at NCSU and the University of Notre Dame before earning his PhD from the College of William and Mary in Virginia in 2014. And he studied in the area of runtime software tools to support adaptive and dynamic large-scale parallel scientific applications. He began his career at Los Alamos National Lab, and now he's moved to Pacific Northwest National Lab from 2010. He currently leads the High Performance Computing Group, where he researches advanced computing architectures and hardware-software co-design methods. He co-leads PNNL's DOE Office of Science-funded Center for Advanced Technology Evaluation project, and is currently the chief scientist on PNNL's internal data model convergent investment portfolio. Okay, I'll let Kevin take it away.
Thank you. Can you see my slides and hear me?
Yes, all good.
Oh, great. Thank you. And thank you for that introduction. My name is Kevin Barker. I am the High Performance Computing Group lead at PNNL. And I just wanted to perhaps give a different topic than what we've been hearing throughout the day in the great talks we've had so far. And I'm going to talk about PNNL's efforts in co-design and co-designing the next generation of intelligent computing systems. And I put intelligent computing systems here, but the methods I'm going to describe and some of the work that I described that's ongoing at PNNL is not restricted to, say, machine learning accelerators or anything like that. These can be more widely applied. And so hopefully these will be of interest to some folks in the audience. Let me see here. So in this talk, I'll just highlight these bullet points here. I'll give an introduction to some of the efforts and capabilities at PNNL. Perhaps folks are familiar with the laboratory and what we do. I'll give a brief introduction. I'll talk about how we kind of see the evolution of capacity computing, and particularly in the DOE scientific computing space, and how things are evolving perhaps beyond what we've seen in traditional high performance computing in the past. That's really been encapsulated in things like the leadership class computing facilities that we see across the DOE National Laboratory Complex. Then I'll talk a little bit about co-design, how co-design as we see it might help us reach some of our goals for advancing the capabilities of computing systems in the post-exascale era, and what exactly that means, and some of the activities that we have ongoing at the laboratory, building a co-design methodology. And then I'll talk a bit about test beds and system prototyping, because that's an area where I do a lot of work and live quite a bit of my time. So, capacity computing and what that is evolving. So capacity computing traditionally means large-scale supercomputing at HPC facilities. These are a lot of times numerical simulations that are used to simulate physical phenomenon in physics, chemistry, biology, or other scientific domain areas. And they tend to incorporate well-established programming models, languages, and tools. Quite a bit of national lab large-scale computing is Fortran, but C and C++ and things like Rust and Julia are also being used. Runtime systems and software toolkits like MPI, the message passing interface, and OpenMP are used to achieve parallelization and concurrency. And that's been exploited to a large degree and evolves from the fact that a lot of the numerical simulations can be efficiently discretized in space and time. And so that leads to a natural progression in how they're mapped to large-scale computing facilities. But a lot of that is changing. AI and ML, deep learning, has been incorporated across the scientific computing world, and the computing ecosystem there is very different. We have languages like Python, toolkits like TensorFlow and PyTorch, and how do those interact with these more traditional MPI, Fortran type ecosystems is not very efficient. And so, we envision, and we are seeing from the scientific computing community, an emergence of what we call converged workflows. So converged workflows really combine elements of high performance computing, AI, ML, and even data and graph analytics into a tightly integrated workflow that is difficult to accelerate, particularly on heterogeneous architectures as we have them today that rely on throughput-oriented accelerators like GPUs to achieve a lot of the flops. And GPUs have been applied very successfully to machine learning, of course, but some of the more sparse or irregular workflows, in particular graph analytics, which is a large area of concern for us at P&L, don't often map well to those throughput-oriented architectures like GPUs. And so that presents a real challenge. And so, you know, in the future, we really see this convergence, and that's really going to be the backdrop for a lot of my talk is that, you know, when I'm talking about co-design and why we need co-design, I'm talking about co-design to accelerate converged workflows. I'll just say it's very hard to beat a GPU for certain types of tensor kernels because they've evolved to support that. But there's a lot of other computing that we're interested in that don't map well to that type of computing paradigm. And that's where I think a lot of what I'm talking about today really is applicable. So co-design is really something enabled by the lead user. And this book by Eric von Hippel has been around for quite a while, called Democratizing Innovation. And this book really introduces the concept of a lead user and how the lead user can really help flip the paradigm of computing development as we've had it up until now. Even looking at the exascale computing program, which is going to result in the deployment of an exascale computer, perhaps later in the year 2021, and then we'll have 3 systems online within 2020, or excuse me, later in 2022, and we'll have 3 systems online within the next 18 months or so. At Argonne National Laboratory, Oak Ridge National Laboratory, and Lawrence Livermore National Laboratory. We've talked about co-design in the context of designing and deploying those systems, but the co-design there is really still an effort where technology in the hardware space and the architecture space has been developed by certain technological vendors, the AMDs, Intels, NVIDIAs of the world. And then it's up to the computational scientists to kind of best understand how their algorithms and software may be able to make best use of those architectural capabilities that are being developed. And part of this is because of the long lead time in developing architectures, right? I mean, it might take quite a few years to develop the next generation of GPU or CPU. And so it's hard to influence those designs and have an impact on the design choices that are made in the development of those architectures unless you're talking 5 years out, right? And that's hard for a customer like the Department of Energy to have a lot of impact there. Typically, what ends up happening is the Department of Energy can do a selection of computing technologies that are being developed. And then we can work on software, system software, application software, compiler tool chains, because those design cycles tend to be a lot shorter. But by the time we see the architecture, a lot of degrees of freedom are already restricted or are already defined. So the lead user concept, though, outlined in this book by Eric von Hippel, really defines the lead user as a source of novel product concepts. And this is kind of the revolutionary idea here, I think. How can users help define all aspects of the system, the hardware software stack, and what technologies are becoming available now that makes that possible that maybe weren't available 10 years ago? So with this kind of open source idea and open source in hardware, innovation comes not only from the manufacturers, but can come from the users. And that has led to new opportunities for user-led innovation in not only computer software, but now in computer architecture as well. Here is just a simple kind of cartoon figure for one of the technologies that's really had an impact in the space, and that's the coarse-grained reconfigurable array, or the CGRA. And that's kind of, I'll contrast it with a technology that's been around for quite a while, the field programmable gate array, or the FPGA. Which has enabled designs to be implemented in hardware for quite some time. The CGRA is a little is quite a bit different from the FPGA, which is programmed at the gate level. The CGRA is really a connection of functional units that can be connected dynamically through a reconfigurable network on chip. And so that opens up the possibility of dynamic reconfiguration. Reconfiguration can be done quickly, which is something that could not be done previously with FPGAs. So at PNNL, we're really using these CGRAs to explore architectural designs, prototypes, and using the reconfigurable aspects itself to perhaps design architectures that might be able to support things like architecture acceleration for different phases of an integrated workflow. And that's something that we're very excited about. So the motivation for architectural research really boils down to a couple of things. Customization or specialization allows higher performance and higher efficiency. A couple of talks today have kind of hit on this topic as well. So this isn't something new here, but we can get higher performance per watt, for instance, and hardware operations to support specific problems at hand. So it opens up a new way to partition hardware, software, and what operations can map to hardware, what operations need to be implemented in software. We can now explore that. Reconfigurability, as I mentioned, serves two purposes: dynamic adaptation, as well as rapid architectural prototyping. And one of the things that we are trying to do at PNNL is engage with technology developers in the industrial area and talk about how can we perhaps get some of the architectural concepts that we developed to support our workloads perhaps integrated into products, and how do we productize some of the concepts that we're developing. The DOE, of course, is not the large player in the large-scale computing space that we once were. I think that's now in the cloud. The Amazons and Microsofts of the world have a lot more sway with the Intels and AMDs than perhaps the DOE does. But productizing some of the designs that we develop is high on our list of priorities, and we're exploring different ways to do that. So what does hardware software co-design look like to us then? And this slide is kind of at a very high level, and we'll dive down into some more specific details as we go. Co-design really requires a two-way flow of information, and that's really the key here. Applications have requirements. Those requirements need to be met, whether it's things like numerical accuracy, quality of service, performance requirements. Those requirements are important and need to be met to be able to effectively support those application domains. And on the flip side, architectures have capabilities that they can provide. What operations can be supported by the hardware, or what operations can be encoded in the hardware, how can that help the applications achieve their requirements? And in the middle of this, co-design is not just a two-way conversation between applications and hardware, but there's also a whole layer of system software. And the system software needs to provide at least these three things: abstraction, expressiveness, and performance. Abstraction being a key for performance portability as well as programming productivity. How can we enable both performance portability and programmer productivity when we're trying to target a wide array of heterogeneous architectures? We don't want to have a world where every application needs to be completely rewritten for every computer that's developed. So how can system software help make those transitions smoother without sacrificing large degrees of performance in order to achieve that? Expressiveness means that algorithms must be able to be efficiently described. And it's no good to have a system support one application or one application domain. At least in our Office of Science Computing areas, there are a lot of scientific domains, and those might have very different requirements and have very different algorithms. And so how can those algorithms be efficiently described to target a single large-scale system? And of course, performance is always key. System software must enable efficient and performant execution of application software. And in the high performance computing world, performance is kind of the bottom line. So we can't sacrifice performance in order to achieve the other goals. In this talk, I'm going to talk a little bit about some of the specific projects that P&L is undergoing or has ongoing that contribute to these goals, and how we're working to build an end-to-end co-design methodology. So this is a little more specific. What does co-design look like in particular? So there's kind of three boxes here. One's kind of orange, one's blue, and one's green. And those correspond to inputs, the co-design cycle itself, and then the outputs. So inputs, we really break down into three large categories. And those here are denoted by application workflow, component design, and then data and system design. And what those are, application workflow really is the algorithmic requirements of the scientific challenge domain. So what are the application requirements? And here things start to get a little bit challenging because we don't want to come, ideally anyway, we don't want to have an application already specified as an implementation in software. Once you start implementing things, you start taking away degrees of freedom in the co-design process. Are you implicitly targeting a cache-based architecture? Well, then you've made a lot of hardware decisions implicitly at that point. So ideally, we would love to be able to define the application workflow from an algorithmic perspective and a requirements perspective. And so that's one area of challenge. I also have here workflow software, though, because in many cases, there are existing legacy software codes that we absolutely have to support. Now, those two areas, algorithmic specifications and workflow software, kind of feed into something that we call a proxy workflow. And a proxy workflow is really a tool that enables communication between application level or domain level computational scientists with the computer scientists and the computer architects that are designing the system. So a proxy workflow might be a simplification of a full-blown scientific workflow, but it needs to capture the salient characteristics of that workflow in terms of computation, data movement, data access, and things like that. And then that workflow is something that's a little bit, or the proxy workflow is something that's a little bit more malleable than the full-blown application code. And so that it can evolve as part of the co-design process. The component design, really, we're thinking about what is the computational substrate at the processor level or the package level, perhaps the memory level, but kind of intra-node. What does the computational substrate look like within the node? What operations are supported by hardware? What needs to be supported by software? We call that the hardware-software partitioning. And those two feed into what's called an abstract machine model. An abstract machine model, it captures the hardware-software characteristics at a high level. And so this could even be boxology, that kind of high level. But it's a communication tool, again, just like the proxy workflow, it's a communication tool for the architects to be able to describe their architecture to the system software community and the algorithm application community. We find that a lot of times the co-design process, you're bringing communities together that aren't particularly used to talking to one another, and they often have different languages, different expectations. And so having these types of tools like abstract machine models and proxy workflows really help bridge that communication gap. Even if that's not something that's directly implemented in silicon, it's something that allows the application designer to get an intuitive understanding. Okay, here's what the architecture is going to look like. Here's how we access memory. Here's the computing operations that are supported and so forth. And then allow the application developer to give feedback, again, because this is a loop, really. The third input is what I call data and system. And this is really thinking about the capacity computing system as a distributed system, not just as something that exists in a machine room. How is data partitioned across this distributed system? In the Office of Science, we're really starting to see systems that incorporate instruments, perhaps light sources, things that exist at a facility somewhere. Those might be connected directly to sensors, maybe intelligent sensors that can do some sort of early filtering. There might be edge computing instrument or edge computing capability located near those instruments. And then those might in turn be connected to some sort of large scale computing facility or perhaps to the cloud. And so you have this kind of a large distributed system. How is that system orchestrated? How is the data partitioned across that system? And then as a result of that, how would computation be partitioned across that system? And then what sorts of capabilities need to exist at the different areas in order to support that necessary computation? That all feeds into a co-design cycle, together with a couple of extra capabilities that I've labeled modeling and simulation and prototypes and test beds. Modeling and simulation and prototypes and test beds allow for rapid evaluation of design trade-offs and perhaps a real-world assessment on physical hardware, perhaps hardware implemented using coarse-grained reconfigurable arrays within some sort of test bed facility. And I'll talk a little bit about the testbed facility we have at PNNL called Senate. I'll talk a bit about that towards the end. But this kind of forms the core of the co-design cycle. And this is really an iterative process that ends when certain metrics are met or certain performance is achieved, at least in simulation. And then the output of that is really an integrated software hardware stack that has the data distribution, workflow software, and system hardware holistically designed within it. So it's a process that in some sense might look a little messy. You know, it certainly is not a waterfall diagram here, but that's not something you see too often in the real world anyway. But it's something that we have started to really employ to good effect in our work. So for the next few slides, I'm going to dive into some specific projects that we have at the laboratory, and these are funded from a variety of funding sources that really fill in different pieces of this kind of co-design process framework. And hopefully this will give you a little bit more insight into how this works. So I'm kind of starting at the top, you know, in a hardware software stack, starting at the top. With software and application software, proxy workflows, and working my way down toward the architecture here. And these are projects that we currently have ongoing that are funded within by two sources. One is an internal investment, I believe was mentioned in my introduction, called the Data Model Convergence Initiative. And that's really a 5-year internal investment made by the laboratory in co-design to support converged workflows. We're currently in year 4 out of 5, and some of these projects have been going for a couple of 3 years now, and they're really starting to bear fruit. And so that's very exciting, and we've had some really good off-ramps for some of these projects that have resulted in some funding from external sources. So ideally, if you're not familiar with how the National Laboratory, what an LDRD is, a Lab Directed Research and Development Project, the goal is really to kind of provide laboratory funding to bootstrap a capability that can then be leveraged to secure external funding, so from a government funding source. And we have had some success here, particularly with this first project that I highlight, which is called Fallacy, which is kind of a funny name, but Fallacy is really looking at, it's really a project that is characterizing and modeling workflows from a data movement perspective. So, you know, if you think about Amdahl's law, right? Amdahl's law is kind of the simple scaling law, but it's very idealized. And in particular, it doesn't really take into consideration costs of data movement and how that might impact performance and scaling. And so that's something that this project Fallacy aims to address. And by doing that, it's developing memory analysis tools, memory profiling tools, and a toolkit that is targeted to provide insight not only to application developers, how is the data of my application laid out? How can we optimize how that data is mapped to physical memory resources, but may also be used to provide insight to intelligent runtime systems. How do we do task scheduling in a distributed environment? How do we weigh the pros and cons of perhaps data movement versus compute capability, and so forth. So that's really one of the goals here of Fallacy. And so some of the challenges of this are, the overheads associated with profiling memory traffic can be very substantial, and so substantial that it impacts application behavior. And so how can we ensure that the profiling that we do does not have a negative impact or cause us to draw conclusions that maybe are artifacts of the profiling itself and are not actual characteristics of the application. And so Fallacy has developed a set of tools that combine dynamic and static analysis, compile time analysis with runtime analysis, intelligent sampling to reduce runtime overhead, and has been able to demonstrate high accuracy with very low overhead, in many cases, single-digit percentage overhead, but with accuracy on par with very high overhead tools like Penn and things like that. So it's been a big success. Because of this work, and the PI here is Andres Marquez, I should mention, because of this work, we have begun a new collaboration with Micron Technologies, the memory manufacturer, looking at new memory designs to support artificial intelligence for science. And so that's a 3-year project that we've just stood up. So that's very exciting. Moving a little bit further down in the stack and talking about proxy workflows of converged applications, I want to mention a project called Pacer that's being led by Cheyenne Ghosh at PNNL. Again, this is under the Data Model Convergence LDRD umbrella. And so the goal of Pacer is really to develop composable proxy workflows that capture key behaviors of various domains of interest. And those might be AI, ML, computational chemistry, graph analytics, sparse linear algebra, and so forth. And so Cheyenne has been working with domain experts who are developing these applications in order to understand how components of high performance computing, AI, ML, and analytics might be integrated to form the converged applications that they're interested in. Some of the specific challenges here are implementations may restrict design spaces for different levels of the hardware software stack. And computational scientists sometimes are very used to dealing with specifics of the software. So stepping back to think about what are the real algorithmic requirements, how can we separate that from a possible implementation is a challenge. But I think that's something that really will lead to big advances in performance down the road. I think the last speaker mentioned, an algorithmic advance will always be an architectural advance. And so if we can take a step back and think about at an algorithmic level instead of at a software level, I think that's really the key to success for this project. And needing to ensure that all salient characteristics are captured. Proxy applications have had a long history in the Department of Energy, going back to the petascale era, when we stood up the first petascale system at Los Alamos National Laboratory in 2008. We really started to explore proxy applications as a way for vendors to interface with computational scientists. And that's been carried forward as we've been developing exascale systems. But a lot of times, at least in the early days, proxy applications would focus on a particular compute kernel. And wouldn't capture data movement, wouldn't capture communication. And so some of the conclusions that were drawn as a result of those proxy applications weren't necessarily accurate when it came time to deploy the full application on the full system. So learning from some of those lessons and incorporating them into this Pacer project has been crucial. And Pacer has really just stood up within the past few months. So we don't have a lot of implementations yet, although Cheyenne is working hard on that. And we do expect to have a suite of proxy workflows or workflow components that we can share. So that will be very exciting as well. The next project I want to highlight is called Duomo, and this is a compiler infrastructure for data model convergence, and this is led by Gochin Kestor at PNNL as the PI. And this is really, as I mentioned, the compiler framework. And the goal really is to develop such a framework capable of generating optimized code for converged workloads, targeting heterogeneous devices and architectures. And so can we use the compiler and leveraging LLVM and the MLIR multi-layer intermediate representation within the LLVM compiler framework? Can we leverage these open source tools and communities to help us accomplish that goal? And so, we're very interested in looking past GPUs, looking more towards customized accelerators for particular workloads. Can the compiler help smooth the transition for the computational scientists to make use of some of these heterogeneous architectures? And that's really the goal here. And she's doing this through a development of a high-level DSL for dense and sparse linear algebra, using things like Einstein notation to represent these operations, and then using successive lowering phases within the compiler framework to target heterogeneous backend architectures. So combining high-level domain-specific optimizations in the front end with a backend that has architecture-specific optimizations into a single compiler flow. She does have open source releases for the compiler itself is known as Comet, C-O-M-E-T, and there is an open source release for that. And she has been engaged heavily with the Google MLIR communities in particular. And so we're excited to get that into the hands of users. So if anyone out there might be interested in how this might help them target emerging heterogeneous architectures, we would love to talk. So finally, getting down to the architecture itself, we have the software-defined architectures for data analytics, or SOTA squared, project that's being led by Antonino Tomeo. And really, this is a project that focuses on hardware design automation and synthesis tool chains to make reconfigurable architectures accessible for applications that are converged, mixing scientific simulation with machine learning and data analytics. And so Antonino and his team have deep experience with high-level synthesis and design automation tools. Primarily, they came originally out of Politecnico di Milano, where Bamboo and Panda have been developed, and they're still heavily involved and engaged with that community and those open source tool chains. So the approach here is investigating novel reconfigurable architectures, or CGRAs, and what are the appropriate abstractions, what are the appropriate interfaces with other high-level frameworks, and how can we explore partial runtime dynamic reconfiguration that these new platforms enable. And so design automation, architectural synthesis, developing a library of architectural templates, and then automatically through a compiler tool chain, lowering high-level, C, C++ implementations of particular algorithms, automatically identifying templates to support those algorithms, and then lowering them down to a synthesizable Verilog. So that's really interesting. There's been quite a bit of open source software releases in this project, tutorials. I believe there's tutorials upcoming at SC. If you're in the design automation community at DAC, there have been some tutorials as well. So happy to share more about this for folks that are interested as well. And then I wanted to touch briefly on architecture testbed capability we have at the laboratory called CENT, or the Center for Advanced Technology Evaluation. And this is really an effort to deploy small-scale testbeds to enable direct assessment of performance, efficiency, and security, as well, metrics of interest, and how those testbed technologies might impact the DOE computing mission down the road. And so this is a project that's funded out of the Department of Energy's Office of Science. So this is not part of the Data Model Convergence Initiative, but it has been funded now. We're in our 7th year, so it's been going for quite some time. And so the mandate by the Department of Energy is really assess how technologies will emerge, or how emerging technologies will impact scientific computing beyond just HPC. So not just looking at large scale facility HPC, but even edge devices, edge computing, and so forth. You know, Senate is really designed to bring a community of users together. So it's something that we would love to engage with anyone who's interested in exploring some of the technologies we have deployed, and as well, computational scientists that may want to understand how their applications might map onto some of these emerging computing devices. Like I mentioned, we established Senate in 2015, and we worked closely with vendors to explore some of the technologies that maybe are a little bit out or a little bit down the road on their roadmaps. We've worked quite a bit with AMD Xilinx, Samba Nova, Next Silicon Graph Core. Those three I can probably lump. If you're not familiar with those three, they are reconfigurable data flow architectures supporting machine learning in the case of Samba Nova and Graph Core, but really HPC in the case of Next Silicon. And I also already mentioned Micron technology and memory. We've worked in the past with IBM, NVIDIA, Data Vortex, others as well. And so these are our systems where, when we can, they're open to the public. If they're not covered by an NDA, we try to open them up to the public and get users using them, get their experiences, and understand also what kinds of technologies might users be interested in that maybe we're not looking at. And maybe we can shift our priorities if that's warranted. Let's see, I'm running a little long on time, so I'll try to speed up here a little bit. Senate contains multiple thrust areas. I kind of mentioned the advanced architectures, but cybersecurity is really an area that our program managers are very interested in. What sorts of attack vectors are opened up by some of these emerging technologies, and particular when you start to have tighter integration, perhaps sharing of resources, sharing of cache levels, sharing of system buses, things like that. What kinds of attack vectors then are opened up, and what might be some strategies for how we might mitigate such things. So, you know, all this talk about homomorphic encryption certainly is very interesting and relevant from this perspective. One particular area of technology that our program manager is very interested in is 5G and advanced wireless networking. You know, and that might be a technology that we can use to stitch together this computing, distributed computing ecosystem, bringing instruments, edge devices, and large-scale facilities together. So how might wireless, advanced wireless communication both enable new science and perhaps open up new security vulnerabilities? So definitely interesting work to be done there. You know, Senate has developed testbed deployments. I'm going to dive into one in a little bit more detail, one of our latest testbeds that I think might be interesting to some folks. We've worked with industrial partners, as I mentioned, computer scientists and computational scientists. So not only bringing the technology in, but how do we develop system software? How do we develop application software to help target those technologies? A lot of times just having some raw piece of hardware is not very informative. There's not a lot of insight to be gained there because we don't have the whole computing ecosystem. You know, we don't have some of the computational libraries already available on those systems. So, you know, that's where we need to engage with the technology developers as well as some of the computational scientists that we have at the laboratory. We've been able to collaborate and foster collaborative partnerships with technology developers, in particular, Samba Nova, Xilinx, AMD. Those have been great partners for us. And we've been able to deploy systems at the lab at PNNL from those vendors, some of them using them in ways that the vendors never really anticipated. So we really help push some of the capabilities on these systems, use them to do things that the original vendors may not have anticipated. Particularly, you know, we get a machine learning accelerator, and the first thing we want to do is high performance computing, scientific computing, and that maybe isn't something that they had thought of as a use case. So we love working with them to try to make things do computations that were not planned, push the envelope a little bit. This is just a timeline of some of the test beds that we've deployed, and I want to spend just a moment to talk about one of the latest ones we have at the lab, and that's this cluster called Junction. A Junction is kind of a small scale cluster, 50 nodes, but it's an interesting cluster. Each node has AMD EPYC processor CPUs, as well as system on chip accelerators as well. And those are, they combine ARM cores with AI. Exciting. We can start to use this concepts that we developed in projects like Soda Squid designing accelerators. So I think this is just kind of looking forward. You know, we're developing all these fundamental technologies. The next step is to really have an end-to-end co-design system, co-design methodologies that integrate these things together. You know, all the way from the high-level proxy applications all the way down to hardware synthesis and hardware design automation tools. And that would be, I think, a capability that would be game-changing for a lot of the computing that we want to do. Particularly as we look beyond exascale. You know, there's probably not going to be a Yada scale or a Zeta scale, whatever the next one is. It's going to be a proliferation of different types of specialized computing infrastructures. And how do we design those, and how do we enable them to be used efficiently? Co-design really, I think, is a key enabler of those technologies. I think I will leave here. I do have my email address here on this last slide. If anyone would like to reach out, please do. I'm happy to answer questions or direct you to people who can better answer the questions. But thank you for your time.
Thanks, Kevin. That was really good. We have maybe just time for one quick question. Augusto Vega from IBM has one question. Is it possible to measure or quantify the quality and presentativeness of a proxy workflow compared to the full-blown real one?
That's an excellent question. And I think that's an area where, you know, we've struggled in the past with proxy workflows. We don't have a rigorous methodology to do that. That's something that I would love to talk about if you have ideas for how that might be done. Really what we end up doing is, you know, kind of looking at performance counters, hardware counters, hardware metrics across both the proxy app and the full-blown application and see how they align. But that's not a great method in terms of rigor, and it's quite ad hoc. So we would love to know if you have thoughts on that.
Okay. All right. Yeah. Thank you so much, Kevin. Unfortunately, we don't have time for more questions, so we will have a slightly shorter 10-minute break, and then we'll convene for the last session. Thanks, everyone.